Chapter 3 deals with information representation. If we want to store decimal number 15, what does it look like? How do we say that this is 15 when in truth all we can do is store a signal of whether electricity passed or didn't. It's on or it's off. There is a signal or there isn't a signal. How then do we represent 15, or for that matter, lowercase k? We start by looking at cells. And in this chapter, you have to be really careful how many bits you have in your cell. Is it a 7-bit cell? Is it an 8-bit cell? A 9-bit cell? Be very careful when you answer the questions. Always know how much room you have. And in this case, we have room for 7 bits. And when we write a bit, we write it on paper as a 1 or a 0. Again, the machine does not store 1s or 0s. It stores the fact that there is an electric current or there isn't. We represent it on paper as a 1 or a 0 because it's the easiest way for us to represent this. But within the machine, it is the passage of an electric current or not. So in 7 bits, we can have these kinds of bit patterns. What we cannot have is this, because there's no way to say a 7 or an 8 when all you can say is yes or no, on or off. There was electricity or there wasn't. And again, when we write this on paper, we write it as a 1 or a 0. A 1 is on, a 0 is off. Why is the bottom one incorrect? Because there has to be a signal in each cell. So you cannot have these cells to the left on this bottom row. You cannot have these empty cells. In this chapter, we have to learn to count in different number systems. We're used to counting in decimal, and in truth, every number system behaves the same way. In decimal, we have 10 digits, starting with 0, ending at 9. And when we want to add 1 to 9, we kind of go back to the 0, but we put a 1 in front of it. So it's 1, 0, 1, 1, 1, 2, all the way down to 1, 9, and add 1 to 1, 9. Again, we start off at the 0, but we put a 2 in front of it. So the first time around, we put 1s in front, and then we put 2s in front, and then we put 3s in front, etc. And this is the same when we count in octal. Octal is base 8. So 0 through 7, I want to add 1 to 7. I go back to the beginning to the 0, but I put a 1 in front. And then when I get to 1, 7, I go back to my 0, but I put a 2 in front, etc. all the way. So it mimics how we do it in decimal. It's just that we only have 8 digits instead of 10. We have 0 through 7. In base 3, again, very similar. But now I only have 0, 1, and 2. Add 1 to 2, I have to go back to my 0 and put a 1 in front. 1, 0, 1, 1, 1, 2. Add 1 to 1, 2. There's my 0, and now I put a 2 in front. 2, 1, 2, 2. Now I add a 1 to that, and I get myself into a bit of a mess because I can't just go back to the 0 and stick a 1 in front again. I have to put a 1, 0 in front. This is like 99, add 1 becomes 100. 101, 102, add 1 to 102, it becomes 110. Why? Because when I add 1, 2, this is like 0, 2. 0, 2, add 1 becomes 1, 0. 0, 2, add 1 becomes 1, 0. We don't often count in base 3. We don't often use base 3. In fact, we will not be using base 3 in this course. We will be using base 2 and base 16. Base 2 is binary. And I'm hoping that you've done this in 112. 0, 1, 1 plus 1 is 1, 0. 1 plus 1, 0 is 1, 1. And then it becomes 1, 0, 0, 101, 110, 111, 1, 0, 0, 0. So if you have not learned to count in binary, now is a good time to learn. And here we have a number in binary, 10110, and we want to know what it is as a decimal number. Let's just move to the next slide and then come back. If I look at a decimal number here, in this column, this 6 is the units place. This 3 here is in the column for the tens. So if I just have 3, 6 is 3 times 10 plus 6, 36. That 0 is in the 100s place, which is 10 times 10. The 8 is in the thousands place, and the 5 is in the 10,000s place. Let's go to Sketchpad. Oh, here is our number. Our 6 is in our units column. The 3 is in the tens, the 0 is in the hundreds, etc. And when we calculate or look at our number, we say, okay, that's 5 times 10,000 plus 8 times 1,000 plus 0 times 100 plus 3 times 10 plus 6. And when I add this all up, that is 50,000 plus 8,000, so 58,036, which is exactly what we instinctively understand this number to be. When we're working with a different number system, such as the binary number system, we do it in exactly the same way. And here we have our binary number, and we do exactly the same thing. When we were working in our decimal system, we multiplied by 10 each time. The tens column, the hundreds column, 10 times 10 is 100, 100 times 10 is 1,000, etc. Now we're multiplying by 2. 1, 2, 4, 8, 16. And what is this number? This is 16 times 1, which is 16, plus 8 times 0, which is 0, plus 4 times 1, which is 4, plus 2 times 1, which is 2, plus 0 times 1, which is 0. And if I add all that up, it is 22. So this is the binary representation of the number 22. And when we go back to our PowerPoint, that's exactly the same number, and this is what it says. And this is the exact same thing. This is the units, the column for 2 to the 0. 2 to the 0 is 1. Then the next column over is the first power of 2, 2 to the 1, 2, 2 squared, 2 cubed, 2 to the 4th, etc. And this was our decimal number 580336. So how do you convert a number from decimal to binary? Here is our number 22. We divide it by 2. That gives me 11, and on this side I am collecting remainders. 11 remainder 0. Divide again by 2. 2 into 11 goes 5, remainder 1. 2 into 5 goes 2, remainder 1. 2 into 2 is 1, remainder 0. 2 into 1 is 0, remainder 1. Once I get a 0 in this column, I am done. And my number is this, going from bottom to top, 1 0 1 1 0. So my number is 1 0 1 1 0, which is 22, and I believe that's what we had previously. 1 0 1 1 0. If I have a 7-bit cell as I do here, then I need to pad it on the left with zeros. Again, this is 22 decimal. Pad it on the left to give me 7 bits. Think we got this? Let's do a little quiz. In the conversions that we've just done, those were all unsigned binary integers. There was no way that we could determine whether they were positive or negative, and so we've just said they're all positive, and right now we don't know how to store or represent a negative integer. We will do in the next section, but for now we don't. So these are all called unsigned, meaning they're all positive, unsigned. You have to know in your homeworks and on tests whether you're dealing with unsigned integers or ones that could possibly be negative. In this next section, we add. So we need to know what our binary addition looks like. 0 plus 0 is 0, 0 plus 1 is 1, and 1 plus 1 is 1, 0. And with that in mind, we should be able to add. And here is an example. Let's try to make this a little bit bigger. We have a 6-bit cell, and we want to add these two numbers. And when we add them in the normal way, we get this. 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0, carry 1. That's the 1 that I carried, and 2 zeros is a 1. So is this correct? So if we convert to decimal, this top number here, it is 26. If I convert the bottom number, it is 17. And if I look at the sum, the answer here, it was 43. And that is correct because 27 and 17 is 43. So we were good. And here's another example. And these were 6 bits. Yes, a 6-bit cell. So you always have to know how many bits you have in your cell. So 6 bits. And I add these two numbers. And I get this. You can take a minute to verify. 0 plus 0 is 0. 1 plus 1 is 0, carry 1. 1 plus 0 plus 0 is a 1. 1 plus 1 is a 0, carry 1. 1 plus 1 is a 0, carry 1. 1 plus 1 is a 0. That's my sixth bit. I've still got to carry 1, but I cannot fit it in my 6 bits. And look what happened. The top number was 42, decimal. The bottom number was 26, and when I add those together, I would like to see 68. But I don't get 68, I get 4. Why? Well, why? Because we do not have room to keep the number 68, to keep its binary equivalent in 6 bits. And when this happens, this is overflow.